To continue with the discussion on superconductivity, I will repeat a few things for your convenience. And so, the sudden drop of resistivity below a certain temperature is called as a superconducting phenomena, or this gives rise to superconductivity, and the temperature below which the resistance vanishes is called as a critical temperature, which is a property of a particular material. And so, the T c, the superconducting transition temperature, is usually of the order of few Kelvin for the conventional superconductors. Now, this we had discussed yesterday, that there are classes of unconventional superconductors, which are also known as high temperature superconductors, and there are not as extensive knowledge about them as they exist for the conventional ones. However, the TCs really vary from a few Kelvin to about 23 Kelvin for this is for NB3 GE. And the features are zero electrical resistance, or resistivity, and no change in crystal structure, and this is verified by X-ray diffraction. Both below T c and above T c, that is in the normal state and in the superconducting state. And third is that it is the state, the superconducting state is characterized by A, conductivity to be infinite, B, the current density to be still finite, C is that the electric field goes to 0, and B is that the magnetic field is constant, and this cannot be explained by classical electrodynamics. Because Ohm's law says that J equal to sigma E. For J to be finite, J is the current density. For J to be finite, sigma has to go to sigma tends to infinity, then E has to be equal to 0. So, this is the third, this is the C condition, and also that curl of E equal to minus del B del T, that gives you B to be constant. This is number D. So, these are some of the features of the superconducting state. Let us now look at Meissner effect. So, the expulsion of the magnetic field from the bulk of the superconducting material is called as Meissner effect. So, this complete and sudden vanishing of the field or rather as the system goes into a superconducting state is really something that is that distinguishes it from an ideal or a perfect metal. Let us see that. So, Meissner, and it is usually known as Meissner effect, but it is also said as Meissner and Ochsenfeld. In 1933, they discovered that there is a complete exclusion of the field lines, magnetic field lines. So, the way the experiment can be done is that one can take a superconducting sample and then put a lot of iron filings around that sample and then apply a magnetic field, and along with that cool the temperature of the specimen, so that it enters into a superconducting state. As it enters, as it is in a superconducting state, then the magnetic fields will be pushed outside the sample, and then the iron filings would get lined up in a regular fashion outside the sample. So, let us think that this is what the sample is like. So, the flux lines will go through this if it is T is greater than T c, and as T becomes, so the iron filings are all scattered in around this superconducting sample, and now as T goes below T c, then these flux lines, the magnetic field lines, are pushed out like this, and because of that the iron filings will nicely align around the superconducting sample. So, this is the tabletop experiment for seeing Meissner effect, and it is seen for superconductors such as lead and tin and so on. Now, in certain materials, it is only above a certain critical magnetic field, which is of the order of a few oersteds, there is no expulsion of the magnetic flux. So, once the superconductivity disappears, the material reverts into the normal resistive state, and the magnetic field fully penetrates through it. And so, there are materials in which magnetic field can penetrate up to a certain extent. Beyond that, if you increase still the value of the strength of the magnetic field, then it gets pushed out. And this is called as a type 2 superconductors, which allows some for some range of magnetic field, for the magnetic field to penetrate inside the sample. Now, let us do a thought experiment of to show the difference between perfect conductor and superconductor. This has been told yesterday, or rather in the last discussion through slides. Just wanted to make it a little more clear by drawing the diagram. So, this is a typical superconductor, and this is a perfect conductor. And so, say the state A is that this is a superconducting materials and this is cooled below T c, and then it becomes superconducting, and then magnetic field is applied, and then there are the expulsion of the magnetic field as we have said, and then magnetic field is withdrawn, superconductor goes back to its original state, no memory. And what happens to a perfect conductor? So, this is a perfect conductor, and so there is an external, it is in an external field. So, it is cooled below T c, the flux still penetrates, but it is resistanceless in presence of magnetic field. Now, when field is withdrawn, it goes into a state which is so this is magnetic field turned off, and it has a memory. So, because the perfect conductor does not have Meissner effect, this is what happens. So, if you compare, so this is A, this is B, this is C, and this is D, and now we have this, let us call it as E, this is F, and this is G. So, if you compare D and G, it is easy to see that a perfect conductor depends on its history, and Meissner effect does not happen in perfect conductor, and that is what distinguishes perfect conductors from superconductors. So, the total exclusion of the magnetic field from the inside of the superconductor is a property which is called as diamagnetism, and you can understand this as follows. So, we have B equal to mu 0 H external plus m. H external is the externally applied magnetic induction. We have not written in vector form, but they are vector equations. So, since B equal to 0 inside a superconductor, the induced m exactly cancels H external. So, susceptibility chi equal to m by H external becomes equal to -1, and as we have said earlier that nothing is more diamagnetic than a superconductor. In fact, in best of the diamagnetic metals have susceptibility which are extremely small, of the order of 10 to the power minus to 10 to the power minus 5 to 10 to the power minus 6. Now, let us look at the electrodynamics on superconductors, and particularly we are going to talk about the penetration depth. So, let us look at penetration depth, and before we do any calculation, let us say that so we have claimed several times that magnetic field is totally expelled, but the fact is that it enters only up to a certain distance, which is called as the penetration depth. Okay. Now, consider the following geometry to compute the distance through which it penetrates. So, this is the superconductor, and one has applied an external magnetic field here, and let us call this direction be x and this direction be y. Okay. So, this is the geometry of the sample. Now, the Maxwell's equations can be written as curl of B equal to mu 0 J s plus del d del t, and curl of B, these are the last two Maxwell's equation, minus del B del t. Okay. So, this is the equation, Maxwell's equation that we all are aware of. This is classical electrodynamics. We are simply doing classical electrodynamics and on superconductors and trying to get some information on how much magnetic field can penetrate inside a sample before it gets completely expelled. So, there is a certain critical depth up to which the magnetic field can penetrate, and this by no means contradicts the statement that we have made earlier, that in superconductor the classical electrodynamic laws are not strictly valid. We are simply trying to get some information out on a quantity called as penetration depth, and to tell you a priori, the reason is that this is one of the important length scales of the problem, and this length scale along with another one called as the coherence length determines the material to be of type 1 or of type 2. So, what happens is that since the displacement current, so let me go through it again. Curl of B is the curl of the magnetic field. This is mu 0 is the permeability, J s is the supercurrent density, and del D del T is the variation of the displacement current density or displacement current, and this is that E and B are the electric and the magnetic fields respectively. Now, the displacement current variation or displacement current rather, this is which is the time derivative of the displacement vector. So, the displacement current is far smaller than the supercurrent. So, in this term you can neglect this one. So, neglect this and write the Maxwell's equations as curl of B equal to mu 0 J s, and J s is nothing but it is equal to N s E V s, which is the super current density is the density of the super electrons multiplied by the electronic charge and the velocity of these super electrons. And the equation of motion of these super electrons can be written as in an electric field to be m v s dot, which is nothing but Newton's law, m v s dot equal to charge times the electric field. in an external electric field that we are talking about. So, if we call this as 1, this as 2 and this as 3, and call these equations maybe as A and B. So, what happens is that if you put 3, or rather if we have if we take differentiate 2 with respect to time. So, J s dot equal to N s E V s dot, and I can replace V s dot from this equation, equation 3. So, N s E square E over m from 3. So, that is the equation for J s dot. So, this is equal to d J s dt. This is how the supercurrent varies with time. Now, if I put 4, let us call this as 4. If I put 4 in B, putting 4 in B, I will have a del B del T, which is equal to minus m by N s E square curl of del J s del T. And this is nothing but, now I will use 4 to replace d J s dt, as this is equal to minus m over N s E square mu 0 curl of del B del T. So, that is curl and curl of this, and hence what we have is that the dB dt, now I can write it as a complete differential, is equal to minus alpha times curl of dB dt. So, this is the equation for dB dt, and alpha is given by m divided by mu naught N s E square. That is what this is defined as alpha. So, now this is written as, the right hand side is written as curl of dB dt. So, this is a gradient and divergence of dB dt, and minus del square dB dt. Now, this term is equal to 0, because one can swap the order of space and time derivative, and can write this as d dt of divergence of B, which one knows by the second Maxwell's equation, that this is equal to 0. So, this term becomes equal to 0, and hence my curl of B or dB dt rather, it is nothing but equal to minus del square times dB dt. So, if you put this into the equation number, let us call it as 5, putting 6 in 5, dB dt is equal to alpha and this and dB dt. So, doing a time integral, this can be written as B equal to alpha del square B. So, this is the equation that gives the space variation of B, and now since the variation according to this diagram, the variation can be in the x direction. So, let us convert this 3-dimensional equation here to one dimension, because we can safely assume that del B, del y and del B del z to be equal to 0, and hence we can write it down as a being equation 7, we can write it down as B x equal to alpha and d 2 dx 2 B x. This is really a partial differential, if you like. It's like del del and so on, and this has a simple solution which is equal to B external. Well, this is like let us not write B external now, we can write it as the solution of this can be written as A exponential minus x over lambda L plus B exponential x over lambda L, where lambda L is nothing but, so alpha is lambda L square, and one can easily see that these because as x goes to 0. So, this superconductor is say from 0 to some d, that is the width of the superconductor. In that case, at x equal to 0, B is equal to B external and so on. So, this can be written as B of x equal to B external x minus lambda L plus B exponential lambda L, and of course, this will blow up as x becomes large. So, we can simply, so this is again, so B external. So, we can only talk about this term, and this term says that the B which is inside, which exists inside the superconducting sample falls off as exponential minus x over lambda L. So, at x equal to lambda L, B x equal to B external divided by E. So, which becomes equal to E minus 1. So, this is called as lambda L is called as the penetration depth. Lambda L is of the order of about 500 angstrom in ordinary or conventional superconductors. All right. So, we will come back to this discussion when we talk about the other energy scale for the superconductors, namely the coherence length, and distinguish between the type 1 and 2 superconductors. Meanwhile, let us do the thermodynamics. So far, we have been doing electrodynamics. Now, let us do thermodynamics of So, thermodynamic route is usually the simplest route to study phase transitions, and so let us consider Gibbs free energy. of a superconductor. So, if the magnetization is M and the magnetic induction is H, then the work done in bringing the superconductor into a region where the magnetic induction H external from with the magnetic induction is H external that exists from a region which is far away where the H external is equal to 0 is given by the work done expression, which I am going to write. Let me write this because these are important points. So, the magnetization is M, and magnetic induction is H. The work done in bringing a superconductor from infinity where H external equal to 0 to a region where H equal to H external exists is given by W equal to minus mu 0, 0 to H external M dH, which is equal to mu 0 H external square over 2. So, that is the work done in order to bring it from infinity to a place where H external magnetic field or magnetic induction exists. So, we have M equal to minus H for a superconductor. So, let us write down the Gibbs free energy. So, Gibbs free energy per unit volume is given by G, let us write it with a G, small g. So, G S, S stands for superconductor in T and at a temperature T and a magnetic induction external, which is equal to G S T 0 and then plus this extra energy that it acquires because of the H external, which is what we have shown here. So, or G S, the same statement, if you want to put it in terms of the magnetic field, it is just there will be a this B external square divided by 2 mu 0 because of the relationship between H. So, your B external equal to mu H mu 0 H external. So, in the normal state, the magnetization is very small. Thus, the magnetic work done is also vanishingly small. Hence, G n T H external equal to G n T 0. So, in the superconducting state, G S T and at a given magnetic field or magnetic induction, there is a extra term B external square by 2 mu 0 or mu 0 H external square by 2. However, in the normal state, the magnetization is known to be very small, and we do not have this magnetic energy contribution as it is seen here. So, now, this tells that equation 1 tells you that there is a B dependence for G s, whereas there is no B dependence for or B or H dependence for G n. So, G n T H external, it increases quadratically with H external. So, it increases quadratically with H external. So, for some H external, equivalently B external, the normal and the superconducting states have same energy, have same Gibbs free energy. So, what it says is that if you plot the Gibbs free energy, so this is Gibbs free energy as a function of either B external or H external, does not matter, they just get scaled by this. And so, for the superconducting state it is like this, and for the normal state it is like this. So, this crossing point is called as H c or B c, depending on which language you want to use. So, below H c, this is that of superconductor S c, and this is normal. So, the S c state, the superconducting state, has lower energy for all values of external field or induction below H c or B c. And as the external field crosses this H c, then the superconducting state has higher energy and the normal state has lower energy, as you can see it here. So, then beyond that the normal state stabilizes. So, what one can look at is that we can call this as equation 1 or rather and this as equation 2. And if we equate 1 and 2 at H equal to H c, H external equal to H c, then G n T 0 minus G s T 0 equal to H c square over 2 mu 0. So, this is positive, and because this is positive the superconducting state is more stable than the normal state below H equal to H c. So, let us give an example. For lead at T equal to 0, Hc equal to 0.08 Tesla. Thus, at T equal to 0, the superconducting state is stabilized by 4.25 into 10 to the power minus 25 joule per mole, and this is really a small energy. So, it is quite amazing that such a small energy actually stabilizes a superconducting state, but that is true of the order of 10 to the power minus 25 joule per mole. Let us now talk about the critical fields. Which is what we have just introduced, and the variation of the critical fields with temperature is given by, we give this without proof, is Hc of T, it's equal to H0. We will tell you what H0 is. It is 1 T 1 minus T by Tc whole square, where H0 equal to H external at T equal to 0. So, this is the externally applied magnetic induction at T equal to 0. So, that is H0. So, it is clear that at T equal to Tc, this term vanishes. So, Hc of T goes to 0. So, there are many things that are important in this particular context, and we have talked about electrodynamics and we have talked about thermodynamics, and we found that some important information is encoded in both of them. Now, let us talk about another interesting comment from Pippard, which is encoded in Pippard's local electrodynamics, or rather non-local electrodynamics, and let us see what it says. If you look at this equation, Js equal to Ns EVs, this is what we have written. This looks like that Js at R is related to Vs at R. So, it is a local equation. So, Js at R is simply determined by the Vs of R at that point R. What Pippard said that the current density at a point R depends on, so Js at R, it depends on E, the electric field at R prime, so which is centered around R in a radius say L. Okay. So, at a given point R, the electric field, the current density at this point will depend upon electric field in the region which is spread all over R prime, where R prime is centered around R with a radius which is L. So, every point inside this circle is R prime, and all of that, those R primes will contribute to the current density at R. So, this is the non-locality which Pippard thought is more relevant and realistic, and this can be thought of to be spread over a region of radius L, and so this L is actually related to the characteristic dimension of the electron wave function. And so this L is related, or rather let us write it, the wave function of electrons should also have similar characteristic dimension, that is extent, which is called as, let us call that as psi, which is called as the coherence length. So, electrons within an energy range KTC, where Tc is the transition temperature, play a major role in pairing. So, this is pairing of electrons So, the momenta of these electrons have an uncertainty of the order of delta p, which is equal to delta E by h. This is V f, which is nothing but k T c over V f. Thus, the position uncertainty. So, we are just using Heisenberg's uncertainty relation. The position uncertainty is delta x is equal to h cross by delta p h cross V f by k T c, thus psi equal to A h cross V f by k T c, where A is a number which is of the order of 1 and A equal to 0.8 in Bcs theory. So, this introduces another length scale for the problem, which is known as the coherence length. So, a coherence length is the second length scale in addition to the penetration depth that we have introduced earlier. So, Pieper suggested that basically that J s at r should be written as an integral rather than writing it as n s into E into V s. So, this is equal to some constant which is not so important. So, this is r dot A r prime, this is that r prime that we were talking about, and r, and this is a r by xi d r prime. So, this is how the non locality in the supercurrent density comes, that the supercurrent density at a given position r depends on the electric field in this particular fashion, that there is a region which is centered around r prime, that every point in that region contributes to the electric field, and a characteristic length scale comes out of it. And we have introduced this earlier. Now, we can talk about dimensionless, introduce a dimensionless parameter kappa, which is equal to lambda by psi, and these are, so for typical superconductors, lambda equal to 500 angstrom, as we have already said, xi equal to about 5000 angstrom. So, kappa is typically less than 1, but however, in 1957 Abrikosov found that for some class of superconductors, this kappa can be greater than 1, and this is used as a distinguishing feature of type 1 and type 2 superconductors. So, to remind you, in type 2 superconductors, the flux lines penetrate the sample till some threshold value of the magnetic field, and if we increase it beyond a certain threshold, then superconductivity disappears. So, a threshold value of kappa for which such flux penetration occurs or starts to occur is kappa, it's say that value of kappa is called kappa c, which is equal to 1 over root 2. So, I mean this is in terms of that. So, okay. So, this says that at this value of kappa, the flux penetration starting at a lower critical field HC1 and reaching an upper critical field So, the scanning tunneling microscope data, STM data confirms penetration of of magnetic flux which are called as vortices, and these vortices actually line up in the form of a hexagonal lattice, in a regular lattice, in the form of an hexagonal lattice, and they arrange in hexagonal lattices, and which are called as Abrikosov lattice. So, we have studied mainly the electrodynamics and thermodynamics of superconductors so far, and have gotten quite a few useful information about superconductors, and the next thing would be doing Bcs theory, which is a microscopic theory of superconductors.